This is my setup and tips for the JetRat-RC SU-57 Felon 30mm dual brushless EDF. Has a 415mm wingspan and is a DIY plug-and-fly kit. This kit was provided to me courtesy of Banggood. I thank them much for sending it for review. I recommend the airframe kit only and not the plug-and-fly kit, as the electronics are not adequate in my opinion. Links to the SU-57 kit as well as the electronics I recommend will be in the pinned comment below the video. The components that I used in mine, the EDF units are a QX motor 30mm EDFs with the 1311 6000 kV motor that's rated for 2S to 4S. The ESCs I used are FET b 20 amp opto ESCs rated for 2S to 4S. The switching voltage regulator I used provides 5 volt 3 amps and is rated for 2S to 6S. The servos I used are the only thing I still have that's stock in this jet, and they are the stock 2-gram servos. In the pinned comment below the video, I have some better 2-gram digital servos. The LiPo that I used was a GMB 3S 11.4 volt lithium high voltage 530 milliamp hour 90C LiPo with an XT30 connector. The gyro I used was a RadioLink BIMD that does internal Elevon mixing, and the receiver was a RadioLink R8FM SBACH/PPM receiver. And speaking of the LiPos, most of my LiPos are standard LiPos, and you charge them at 4.2 volts per cell. I didn't think about it, but since this battery that I used is a lithium high voltage battery, I should have charged them at 4.35 volts per cell. That would have given me more power from the first launch and would also have provided me with a little longer flight time. So the LiPos that I have listed in the pinned comment below the video are not only a higher capacity than the one that I used, which will give you a longer flight time, but they're also LiHV, lithium high voltage, for the 3S and the 4S LiPos. So links to those are in the pinned comment below the video. And speaking of the batteries, here are the battery bay dimensions. Okay, 75 millimeters in length by 30 millimeters width by 21 millimeters deep. So if you do not use the LiPos, the 3 and 4S LiPos that I have listed in the pinned comment below the video, make sure that whatever you select to use is within the size parameters that I have listed here. The assembly guide is fairly well thought out and allowed me to build the airframe without any difficulty. I did publish some images of my build log on our Facebook page that chronicled some of the build. Not all of it, but some of it. A link to the assembly guide, which is a PDF manual, is in the pinned comment below the video, so you can download the assembly guide. You might want to take a look at the images that I posted in my build log on our Facebook page, because it will supplement the images that are in the assembly guide and may be helpful to you. All right, so CG. I don't remember how I found this diagram here, but it was not in the assembly guide, the PDF manual that you can download. But I came across this on one of their posts, and it said, you know, in the assembly guide, if I remember correctly, it said CG is located at the red star in the diagram. And I thought, I went through the entire assembly guide, and I couldn't find anything that showed a red star on the diagram that specified the CG. The only red stars I saw were the ones that are here on the wingtips, and obviously that's not where the CG needs to be. So I took this image and I scaled it up so that between the length of the tip of the nose to the tip of the tail was 580 millimeters as it specifies. And then I measured from the tip of the nose to the center of this star, and I came up with 320 millimeters from the nose. The CG that I was using on mine is 310 millimeters from the nose, and that worked very well, except there were a couple of times where I got really slow in a turn where it felt like it was just a tick tail heavy. My advice would be that when you set yours up, set your initial CG to 305 millimeters from the tip of the nose, and if it feels slightly nose heavy, go ahead and move it back to 310 millimeters. But I would start off at 305 millimeters. All right, so your radio setup for your control surfaces, and we're gonna go over real quickly the nomenclature I'm using for this. So there's only 2 servos, right? You have 4 control surfaces, but you only have 2 servos. So there's elevon mixing with what would normally be the ailerons and the elevators, okay? So I'm going to refer to what we would normally call the ailerons as the forward position elevons, and what we would normally refer to as the elevators as the aft position elevons, okay? So on my forward position elevons, which we would normally call ailerons, using the aileron control stick, I had 15 millimeters of deflection with an expo of 55%. Using the elevator control, I have 14 millimeters of deflection up and down on both of these with an expo of 55%. When the sticks are centered, the forward elevons, aka the ailerons, are in a neutral position when the sticks are centered, which means that the trailing edge of the ailerons are in line with the trailing edge of the wing plate. Okay, so the elevons in the aft position. Using the aileron control, I have 19 millimeters of deflection up and down with an expo of 55%. With the elevator control, I have 18 millimeters of deflection with 55% expo. I have 2 millimeters of positive reflex with the sticks centered on the aft elevons, which means that they are 2 millimeters above what would normally be neutral. Okay, I found that that was required on my build for it to travel and maintain its attitude at cruising speed. So set yours up that way and then test it and see what you need to adjust. All right, and now my tips for this. The control linkage is set up as specified in the assembly guide. I didn't deviate from that. Carbon reinforcement is needed for the aft elevon control rods. So the control rods are only 0.8 millimeter in diameter, steel control rods. They're quite lengthy, going from where the servo arms are located to the control horns on the aft elevons, aka the elevators, compared to the forward elevons, aka the ailerons. And I found that when I was performing a roll in my first test flight, where I was using the stock ESCs, so I didn't have a lot of power and I didn't have a lot of speed. So when I gave it full deflection for a roll, it would roll pretty quickly until it became inverted, and then it would pause, and then it would complete the roll. So what was happening was the aft elevon control rods were actually flexing on me. So I took a 1 millimeter diameter carbon tube. The inside diameter is 1 millimeter, so it fits like a glove over top of the control rod. And I cut them a length about 75% of the length of the control rod. And then in my second test flight session, where I had a lot more power and a lot more speed, I was able to perform a full stick deflection roll, and it rolled very fast, and it didn't pause. So I know that the control rod was no longer flexing, and it was nice and tight and axial. So there's no doubt in my mind that you do need some carbon reinforcement for those control rods. I also recommend that you do some carbon reinforcement of the main wing using A-frame. So in the kit, you have a single carbon slat that is forward of your EDF pods here, your nacelles. And it doesn't go all the way to the wingtip, right? And it is forward of where the widest part of the wing is. What I recommend is you take 2 more carbon slats, and you see where this seam is right here. This is where my CG is located, right here where this seam is. I would start the carbon slat there, and I would run it across the carbon slat that they gave you, where you installed it, and run it halfway across the shaded area on the wingtip on both sides. And then I think you're going to have a jet that will no longer have any wing flexing when you're doing high-speed dives. What I found with mine was, if I was doing a big wide loop, if I was doing a split S maneuver, or I was doing an Immelman, and I was doing a high-speed dive when completing that aerobatic maneuver, I would get some wing flexing, more on the right-hand side than on the left-hand side. And so every time that I came out of one of those maneuvers with too much speed, it would break to the right because the right wing was flexing more than the left wing. And so it wasn't holding as much lift, and it would break to the right. So I recommend doing that. For the elevon hinges, the aft elevons, I recommend using rigid plastic hinges for those hinge lines. What I did with mine was, it has those little foam hinges, and I reinforced those hinges with packing tape. And that works well, except that the foam and tape hinges will flex because these control surfaces on the aft elevons are very large. And so there's a lot of force, from the wind being applied to those. And as you can see, there's a lot of that control surface that is outside of where the hinge line is. And so you get some axial twisting on that control hinge. I recommend that you use rigid plastic hinges for that, so that you don't get that flexing on the hinge line. And so it makes the airframe more predictable and more stable doing that. My launch throttle is 100%, but a slightly upward angle with a moderate chuck, and it takes right off. Okay. All right, so that is my setup, and those are my tips for you from my build experience and my test flights on this airframe. It's a very good airframe. It looks really, really nice in the air. It handles very well. Mine, with the power system that I have, my all-up weight is 205 grams. I get 250 grams of thrust, which gives me a 1.2 to 1 thrust-to-weight ratio, and that is just charging the LiPo at 4.2 volts per cell. If you acquire the LIHV LiPos that I have in the pinned comment below the video, then you will have a slightly better, probably a 1.25 to 1 thrust-to-weight ratio, which will enable you to do nice aerobatics with it and a very good vertical climb out. So that is a wrap on this episode. Stay tuned, and I will see you in the air.